All right. This presentation is about the privacy-preserving machine learning competition organized by Criteo in the context of at KDD 2021, and what was our solution for the second place in the clicks task. So, as a quick overview, we'll talk about our data preprocessing, where we enrich the granular data by using the aggregated noisy data. And we'll also go over our models and how we created them. And finally, over what we believe is the most interesting part of our solution, that is how we adjusted our model predictions using the aggregate data to obtain a better solution. Next slide, please. Thank you. So for the singles aggregated data, which were noisy given the differential privacy used, this means we had a series of feature and value pairs where it was possible to obtain an estimated click-through rate, or CTR, and this provided us with 19 features. Now, for the aggregated pairs, we have the same structure, except we had all the pairwise combinations of those 19 features, so we ended up with 171 features from those pairs. Next slide, please. Thank you. So after having processed the aggregate singles and the aggregate pairs, we proceeded to take those 190 features to add a little over 20 new features by using weighted means of the already preprocessed aggregate features, as you can see described here in the code. So some details about preprocessing. We did it independently uh, for each model. So that means we were able to tune the parameters of preprocessing for each one of the models to gain the best performance possible from each of them. Also, the click-through rate estimates for the aggregated singles and the aggregated pairs was regularized so that it did not stray too far off from what was the global mean of the CTR. And the estimated CTR was always bounded between 0 and 1 so that we can have a negative CTR or maybe one above 100%. Now, estimated CTRs that were or would have been produced where counts were less than 200 or around 200, depending on the model. We ignored those in order to reduce the noise. Now, we did take a few approaches when the CTR estimate was missing because one of the necessary inputs to compute it was missing. Um, so when the model could handle missing values, for example, gradient boosted decision trees, we did let them go through, as that could provide useful information by itself. But for other models, such as the neural network that we used, if the pair was missing, uh, but the singles was available, then we imputed it using the singles. However, generally we did impute the missing value based on the column average. So in summary, we combined the estimates from the aggregated singles, the aggregated pairs, and the average we added at the end. Now, as for modeling, we were lucky to have access to AWS Batch. That meant we could iterate very quickly on our models, and each of us could easily run multiple experiments at a time, test different parameters, hyperparameters, collect those results, improve based on the analysis of these results, and repeat the process iteratively over and over again. Now, our first and best performing model on its own was gradient boosted decision trees, where the algorithm for finding the best splits was histogram based. We settled on 250 iterations with the default learning rate of 0.1 and max step for the trees of 5 and ELF2 regularization. And we then bagged this model 240 times in samples, but also to a lesser extent in features. And bagging it more times would probably have increased the performance a little further, but it was becoming computationally expensive. And at that point, we had to make choices given the time constraint. For our second model, we used a neural network with 4 hidden layers of 16 neurons each. For this we used the rectified linear unit activation function, and the model was bagged in the same way as the gradient boosted decision trees. We used vanilla L2 regularization for this neural network, and we did create other better performing models that used dropout and other architecture, but they were more correlated with the gradient boosted decision trees. So final ensemble was actually not as performant as it was with this particular neural network. So this is the one we kept. Now, final ensemble, at some point we tried stacking models and other things, but we figured out the what worked best for us was a weighted average, where the gradient boosted decision trees accounted for roughly 60% of the prediction and the neural network accounted for the rest. Now, as for our validation strategy, we went with the classic five-fold cross validation. And for this, our general rule was that ideally we would see at least four of the five folds improving in score. As for hyperparameter search, we we mostly iterate on the parameters manually, but we also use grid search and randomized search to compare during our iteration. Now the weights were for the ensemble were found with an automated brute force search. It was testing a high amount of permutations, and it also included weight zero, which allowed us to sometimes drop models that were good by themselves but were not necessarily beneficial for the ensemble. Now, for the final and more interesting part of our strategy, Matt, it's all yours.
Thanks, Marco. So at this point in the competition, we were in the mix for a spot in the top three, but we needed a little bit more to get beyond some of the other great teams. So with about 3 days left, we had this idea for adjusting our predictions, which I'm going to tell you about now. Because we did kind of come up with this idea pretty late in the competition, it's a little bit unpolished, and there's probably ways to improve it. But we can talk about those more a little later. So the motivation for prediction adjustment is basically the following question, which is, are our predictions consistent with the aggregate data? So, for example, if our modeling predicted observations with feature F had an average CTR of 0.15, is this close to what the aggregate data says? So if we look in the aggregate data for that feature or feature pair, and we pull out its CTR, is it close to 0.15? That's kind of the motivating question. And I should credit Bartek here because he is the father of this idea. So we kind of thought about our prediction adjustment problem as two competing goals. So the first goal is to make our classical ML predictions that Marco just described agree more closely with the aggregate data. The second goal we had was to not change our predictions too much because they were already competitive. So here's kind of those two goals pictorially. On the bottom left, we have our best classical machine learning predictions. Those are based on 102,000 observations, granular observations. And then in the upper right, we have our aggregated data. It's based on something like 88 million aggregated observations. But we just generally found the aggregate data a little more difficult to use than the granular data. So we wanted to sort of get the best of both worlds and better leverage the aggregate data. And that's kind of where these two guys shaking hands in the middle, that they're compromising. So we wanted to find some kind of middle ground, some kind of compromise between our best predictions that were based on the small number of granular observations and kind of better estimates of CTR coming from the aggregated observations. So in order to explain our method, I'm going to have to introduce some notation. So just bear with me. So it's a little boring, but just, yeah, bear with me. So the first thing we have to do is we have to fix an ordering of all of the feature and feature pairs. Once we have that ordering, we can describe this matrix M. So this matrix M is 0 everywhere, except in places where the ith feature of our feature ordering is relevant to the jth observation in the matrix that we're predicting on X test. In those cases, Mij is 1. Now that we have M, we can talk about M prime, which is just a version of M whose rows sum to 1. We also need to introduce this vector C. C is for CTR. The ith entry of C is the CTR estimate derived from the aggregate data corresponding to the ith feature of our feature ordering. And as a small note here, a small detail, the CTR estimates in C were regularized and thresholded as Marco described before for the classical predictions. Just a couple more pieces of notation. So we're going to call X the vector of CTR predictions for observations in X test that we're going to find by optimization. We're going to call P the vector of CTR predictions for observation in X test found by the classical machine learning methods Marco just described. So at a high level, we're kind of going to modify P, and it's going to become, the modified version of P is X, and we're going to find X by optimization. That's kind of what we're doing at a high level. And finally, last piece of notation is sigma is the familiar logistic function. So we described our goals in words. Now we're going to describe them in mathematical notation. So our first goal was to make the aggregate data consistent with our predictions. And there's different ways of doing this, but this was what that meant to us. So it meant making the following quantities small. M prime X minus C. So M prime X represents the aggregates that the prediction vector X is associated with, and C represents the true aggregates kind of given to us in the aggregate data. We want those two quantities to be close for every feature and feature pair. So our second goal was to not modify our classically estimated CTRs too much. So again, there's different ways to formulate this mathematically, but to us that meant making the following quantity small. So this first term is our predictions, our modified predictions that we're trying to come up with in logit space. And the second term is our best classical predictions in logit space. So we want our best classical predictions to be close to our best modified predictions in logit space. That's what it meant to not change our predictions too much for us. And again, there's different ways to kind of translate those words into math that are interesting and possibly worth exploring in the future. So why do we use logit space? So the answer to this is at first we didn't. At first we just wanted X to be close to P in prediction space, probability space. But what we found was that our optimal vector X ended up having zeros and ones in it, which are sort of unrealistic. So yeah, that's why we use logit space here to define the distance. And yeah, this kind of equality on the right, that's just different notation to make it more concise and kind of make it look more like a norm. Okay, yeah, so combining these objectives, we solve the following optimization problem. So the first term we talked about will push our predictions to be consistent with the aggregate data. The second term is going to prevent our predictions from being too different from predictions we know are good. And when we solve this optimization problem, we get an optimal x star, which turns out to be better predictions for the observations in X test than our previous best predictions, which was the vector p. So yeah, that's kind of the details of prediction adjustment. But like I said, it's a new technique that we haven't really fleshed out fully. So we kind of have a few questions or directions of exploration that might be interesting. So the first one is there a way to incorporate the consistency with aggregates as a kind of regularization for classical machine learning models? Another question we have is, do other norms for either of our two goals, do they provide better results? We only got to try so many in the time we had. Another question we had was, can counts better be incorporated into the notion of consistency with the aggregate data? So you might weight certain components of one of these resulting vectors higher if the count is higher or something like that. I think there might be something possible there. Another question we had is there a way to do prediction adjustment on a prediction by prediction basis rather than as a batch optimization problem? Being able to do this on a prediction by prediction basis would make this much more useful in the real world, where observations kind of come in one by one and you don't have the opportunity to collect a batch and solve a batch optimization problem. So our takeaways from the entire competition are as follows. So the first takeaway we had was that we were surprised by the fact that we were able to get fairly strong performance with just kind of classical machine learning techniques and 102,000 granular observations. So another takeaway was that it was difficult to use the aggregated data effectively. We tried some things directly using it, and none of them worked great. At least until the final days of the competition, when we kind of had this prediction adjustment, which does directly use the aggregate data. And the final takeaway was that I alluded to this earlier, that there's probably ways that the prediction adjustment idea can be developed to make it better and more useful. But that was I think our most interesting contribution to this competition. Yeah, so thank you very much.